Hi all, welcome to the demonstration of TotaleNodeB solution over Octasic OCPTS 3000 platform. Before we see the demonstration, we will briefly run through the overview explaining the TotaleNodeB architecture overview, salient features of the TotaleNodeB solution over Octasic, mode of operation between L2 and Phi, the end-to-end validation setup, and the call flow that we will be demonstrating. The TotaleNodeB is a software solution from Radisys that is enabled on different platforms. The following diagram shows the different functional blocks in the TotaleNodeB. It comprises of 3GPP or RFC compliant protocol stacks and an application part. The application includes modules like radio resource management, self-organizing network, radio environment monitoring, and timing modules. The solution also comprises of an integrated OEM for configuration and management purposes. Now let us look into the TotaleNodeB product architecture overview. OEM module is responsible for configuring and managing the eNodeB from HEMS. Currently, it supports TR-069 issue 2 and TR-196 standards. This module is the central controller within the HENB and derives the top-level state machine and tasks carried out in the HENB. This module interfaces and controls various OEM components like TR-069 client, command line interface, IPsec client controller, FTP client controller, and messaging entity. The self-organizing network or SON module uses the radio environment monitoring or REM module scan results for self-configuration of the cell at startup. The REM scan results are used by SON for frequency selection, PCI selection, and automatic neighbor relation. The Radio Resource Manager, eNodeB application, and the protocol stacks implement all the eNodeB and UV related procedures. These include radio bearer control, radio admission control, connection mobility control, dynamic allocation of resources to UVs in both uplink and downlink, IP header compression and encryption of user data stream, selection of an MME for the UV, routing of user plane data towards the serving gateway, scheduling and transmission of paging messages, scheduling and transmission of broadcast messages, measurement and measurement report configuration for mobility and scheduling. The convergence layer abstracts the interface to the physical layer, which is an external component from the MAC layer. The convergence layer maps the MAC lower interface API to the physical layer L1 API. This layer abstracts the transport that is used to communicate with the Phi. The physical layer L1 API is a FAPI compliant interface defined by Femto Forum, with slight deviations as required by the Phi platform. TotaleNodeB software solution is highly portable, since it requires only a change in the convergence layer as required by the Phi platform. The TotaleNodeB software solution enabled on Octasic platform is based on the GA 3.0 release version of the base product. The following table summarizes the TotaleNodeB over Octasic solution in comparison with the base product capabilities. The salient features of the TotaleNodeB on Octasic platform are: frequency division duplex mode of operation is supported. The peak throughput in DL is 14.5 Mbps and in UL it is 1.5 Mbps. CISO transmission mode is supported in downlink and uplink. Max scheduler uses round-robin scheduling. One user per TTI is supported. The throughput numbers, transmission mode, and number of users per TTI is a file limitation at this point. After this presentation, we will show a demonstration with 4 users doing a simultaneous data session. The following diagram shows the mode of operation between TotaleNodeB software, which implements the L2, L3, and the Phi. The L2, L3 runs on an external PC and communicates with the Phi over a gigabit Ethernet interface. This diagram shows the end-to-end setup. The third-party EPC, the video or data server, the machine on which the TotaleNodeB software is running are all connected to a switch. The OCPTS 3000 on which the LTE-5 is running is connected to the TotaleNodeB machine via a gigabit Ethernet link. The UVs are connected to the OCPTS 3000 over the air. This table summarizes the UV models that are used for the test and the TotaleNodeB host machine configuration. To get NAS level services from the network, NAS nodes in the network have to know about the UV. To facilitate this, UV has to initiate attach procedure, which is mandatory for the UV at power on and also during initial network access. Once the attach procedure succeeds, a context is established for the UV in the MME, and a default bearer is established between the UV and the PDN gateway, and an IP address is allocated to it. Now that the UV has IP connectivity, it can start using IP-based Internet services or IMS services if IMS network is available and if the UV has a subscription for the same. UV first establishes the RRC connection with the eNodeB. UV sends the attach request message together with the PDN connectivity request for the PDN connectivity on the established RRC connection. MME updates the location of the UV in the HSS and establishes a GTP tunnel with the P gateway. An IP address is allocated to the UV. If the network is not able to identify the UV, an identification followed by authentication and security mode procedures are completed. MME sends an initial context setup request to establish the bearer between the S gateway and the eNodeB. Following the access stratum level security mode procedure, the eNodeB reconfigures the resources to the UV by sending an RRC reconfiguration request to the UV. In this message, the eNodeB piggybacks the activate default EPS bearer context request NAS message to the UV. The UV updates its RRC connection configuration and responds back with RRC connection reconfiguration complete. The eNodeB now sends initial context setup response to the MME. The MME sends eGTP modify bearer request to the S gateway to update the eNodeB tunnel ID for the default bearer. After updating the information, the S gateway responds with modify bearer response to the MME. The MME now sends attach accept and activate default bearer context request NAS message to the UV. If the MME has allocated globally unique temporary identifier while sending attach accept, the UV needs to process it and give back the attach complete as a response to it. The UV piggybacks the activate default EPS bearer context accept NAS message to the MME. This completes the attach and default bearer setup procedure. Let us see a live demonstration of 4 UVs doing an active download session on OCPTS 3000 board. This is an end-to-end setup. This OCPTS board on which the LTE-5 is running is connected to the host machine on which the TotaleNodeB is running via a gigabit Ethernet link. The LTE-5 operates in FDD mode. It supports single input, single output transmission mode and one user per TTI. We are currently operating in 10 MHz bandwidth and LTE band 20. These are the 4 UVs. 3 of them are Huawei dongles and one is LTE Galaxy S3. All the UVs are category 4 UVs. This machine is remotely connected to the Polaris EPC and the data server. We're already doing an active data session with 3 LTE dongles. 3.5 Mbps UDP traffic is currently being pumped in the downlink for each of these UVs. We can see that the active number of UVs is 3 and the aggregate throughput in the downlink is 10.5 Mbps. Now we will attach the 4th UV and start a data session on it. The UV is now attached and we can see the S1 AP messages between the eNodeB and the MME. Following the attach request and PDN connectivity request, the authentication and security mode procedures are done. In the initial context setup message, an IP address is allocated to the UV. The attach complete and activate default bearer context accept message completes the default bearer setup procedure. We will pump 3.5 Mbps DL traffic from the data server for this UV.
Now we are seeing that the active number of UVs is 4 and the average throughput in the downlink is around 14 Mbps. The peak throughput we observe is 14.5 Mbps under lab conditions.
For more videos and solution demonstrations, please visit www.radisys.com. Thank you.